Okay, so fair warning, this is going to be a long one, and you need to have your calculator handy. We're going to talk about something called an improper integral, but before we do that, I just want to go through an exploratory process of what exactly we're going to be doing. So you guys know in Algebra 2, you learned the graph of 1 over x, okay? So here is something 1 over x. One of the cool features of 1 over x is that it is unbounded, meaning this kind of goes up forever and forever and forever and goes out to the side forever and forever. But what if we just start at 1, and if we were able to find the area under the curve from 1 to infinity of this graph 1 over x dx. So here, forever and forever and forever. Now, counterintuitively, we might look at it and say, there's no possible way that we could find this area under the curve because this goes on forever and forever and forever and forever in this direction, and it is unbounded. So continuing on forever and forever. So what I want to do is start by kind of faking my calculator into thinking I have infinity. Now, obviously, your calculator will not evaluate this integral if you go to Math 9. Number one, you don't have an infinity button unless you have a TI-89. And I can't really type in infinity. So we're going to fake our calculator into thinking infinity. I can type in successively larger values like 100, 1,000, and 1 million into my calculator and use Math 9 and come up with values. And so I actually want you to press pause on me, go type them in your calculator, and see if you can fake your calculator into thinking you are approaching infinite values by going 100, 1,000, 1 million, and writing those values for the area under the curve. So if you're joining me, let's check what you've got. You should have about 4.605, 6.908, and about 13.816. Now, I don't see any real trend in these numbers. These numbers appear to be getting bigger, and it should be, because as I'm moving along my x-axis, I am accumulating more area. So this is pretty intuitive. So the question says, do you think that this integral converges or diverges? Now, we haven't really talked about these two words before, but I want you to know the word diverges means no finite value or no finite area in this case. So these numbers don't appear to be trending towards anything. If we had to guess, we would probably say that they diverge because these numbers are getting bigger and bigger as we're accumulating more area. But maybe let's look at something that does something a little bit different. So now we're going to look at an integral starting at 1, going on forever and forever, of e to the negative x. Okay? Now, e to the negative x, it's not a graph we encounter very often, but it is basically a decaying e to the x function. And what we're going to do is we're going to start at 1, and we're going to talk about this area under the curve. Now, you know that e to the x has a horizontal asymptote at 0, so it's going to get really, really close, just like the previous function we did. And so that area goes on forever and forever. And again, we can't type in infinity into our calculator, so we're going to fake our calculator into thinking infinity. So I want you to press pause. I want you to do a Math 9 integral going to 100 to 1,000, and honestly, that should be enough. And don't press play again until you've got those two numbers. Okay, so if you're coming back, let's see what you got. Should be about 0.36788, and this one ends up being 0.36788, and pretty close values. So if you had to guess, the bigger I make that number, you could even test it. You could type in 10,000 or 1 million, but it honestly looks like it is converging to a value. It is approaching a specific number. So we would say that this converges. And it's weird because if it converges, that means this has an area under the curve. So here is something that has no bound. That area continues on infinitely so, but this has a finite area, a summable area. And in fact, that area happens to be about 0.3679, which is equal to 1 over E. And we'll talk about why that happens in a moment. So if you were to graph these two graphs on your calculator, and what I'd really encourage you to do is to press pause on me and try it. If you press pause on me and you graph 1 over x, and you also graph e to the negative x, why does one of these both have unbounded area, but why does one have a finite area under the curve and the other one doesn't? And so if we first look at these on the window from 0 to 5 and negative 1 to 2, okay? So if we say here is 5, and I'm going to make quick sketches just to be really quick for time, okay? And I'm going to graph them on top of each other, even though I've given you 4 graphs here. If you guys graph 1 over x, you get something that kind of looks like this. So this is the graph of 1 over x. And if you were to graph e to the negative x, you get something that looks like this. Now, we're talking about the area under the curve starting at a y value of 1. And one of the things I want you to notice is that it appears that e to the negative x gets really small really fast and gets closer and closer to that x-axis really fast. And this becomes even more obvious if we change our window to say maybe 100 to 500. So if you were to start at a value of 100 and stop at 500 and scale your y values from negative 0.0001 and stop at 0.01, what's interesting is that we get the following. 1 over x still looks like this, and the graph of e to the negative x on this window looks like this. And so when we talk about area under the curve, especially area under the curve all the way out to infinity, notice how close to the graph, close to the x-axis, that e to the negative x is. So why is it that two graphs, both with infinite bounds, they both have asymptotes, they're both getting closer and closer to 0, why does one have a finite area and the other one doesn't? And the reason is because e to the negative x gets small quicker. Therefore, area gets closer and closer to 0 and becomes negligible. 1 over x gets small, but it doesn't get small quick enough. Now, this seems kind of abstract, and you're like, well, how will I know if it gets quick enough? How will I know if it has finite area? Obviously, this is just an exploration of this fact. We're going to actually approach this from a mathematical standpoint. So, improper integrals, there are 2 types. We're going to start by talking about a type 1 improper integral. A type 1 improper integral is an integral with infinity in your limit of integration. So anytime you see an infinity in my bound, either in the top, in the bottom, or sometimes even in both, the title for those are called improper integrals. And we're going to approach them one of 3 ways. Okay? If you see an integral from a to infinity of a function, we're going to insert a dummy variable and set up a limit, because remember that infinity is only a concept that we're able to work with inside of a limit. So we're going to say the limit as b approaches infinity, integral from a to b of f of x dx. So basically what I'm doing is I'm replacing the infinity with a letter, and I'm setting up a limit approaching what was there. Now, let's say that you have an integral with a negative infinity stopping at some number. Again, we're going to replace it with a limit. We're going to approach what it originally was there. And instead of the infinity, we're going to insert the letter. And we're removing infinity from the integral. So again, there was a negative infinity here. Now I've set up my limit to approach it. Probably the trickiest one of all three of these is when you have negative infinity and positive infinity in your bounds. In which case, we're going to start by splitting it at a c value. So we're going to go from negative infinity to c, and from c to positive infinity. And then once you have split these, we can now turn it into our two cases. We can say the limit as a approaches negative infinity, integral from a to c of f of x dx, plus the limit as b approaches positive infinity, integral from c to b of f of x dx. So, fun facts. Yes, you have to know how to set these up. Yes, you must write limit with them and get rid of the infinity by setting up a dummy variable. Now, I know that I used a's and b's in here, but you're going to see me just use b to keep things simple. Honestly, you could use any letter you wanted, but we're making a dummy variable, okay? So we're going to start with the example we just worked with. Now, the integral from 1 to infinity of 1 over x dx, and you'll immediately notice there's an infinity in the upper bound. So an infinity in my upper bound, you know, because we just did this a minute ago, this thing diverges. But how do I prove that mathematically? So step one, I have an infinity in the upper bound, so I'm going to say it is equal to a limit as b approaches infinity from 1, and instead of the infinity there, I'm going to put the letter b, okay? And so make sure your limit variable matches your bound variable, okay? Of 1 over x dx. Now, guys, you're going to work this integral from the inside out. You're going to do the integral first. You're going to sub bounds second. The limit is last. Always evaluating the limit last. Integral first, sub your bounds, limit is last. So I'm going to demonstrate that. At every step along the way, you have to write limit until you've evaluated the limit. Notationally, this is an easy place to super mess up, guys. You've got to be super careful about going step by step and showing all of your steps. So we're going to do the integral. The antiderivative of 1 over x is the natural log absolute value of x. So I've taken my integral. I still have bounds from 1 to b. So integral is first, bounds are second. So limit as b approaches infinity, I'm going to sub in my bounds. I'm going to say the natural log of b minus the natural log of 1. Okay? Now you know that the natural log of 1 is 0, so I don't have to write that again. So I have the limit as b approaches infinity of the natural log of the absolute value of b. Okay? The limit is the very last thing we're going to evaluate. So we have the natural log of infinity. I'm directly substituting in infinity. Now remember that the graph of the natural log of x as I go towards infinity grows and grows and grows and grows ever so slowly. So this is going to infinity. So here is something that is an infinite limit. Now, a limit that goes to infinity does not exist. So this diverges. The area under this curve is divergent. So we're going to say our conclusion is that the integral diverges. And we can't just leave our answer as equals infinity. Your answer is that the integral diverges. Your answer is not the infinity. The infinity provides me with the answer that the integral diverges. Okay, so let's do another one. Now look at the second example. Again, I have an infinity in the upper bound, and this is already an example we did on the previous page in our exploration. We know that this integral is going to converge, but let's talk about the math as to why. So, step number 1, we're going to write a limit. I'm going to use a dummy variable of b approaching infinity, the integral from 1 to b, and I won't always use 1, this just happens that both of these examples used 1, of e to the negative x dx. Now guys, you still have to know how to take an antiderivative. You still need to know how to work with limits. All of this is prerequisite knowledge, okay? So if I'm just looking at this integral, this is something that would make me do u substitution in. We would say that u is negative x and du is negative dx. So negative du is equal to dx. And so this becomes the limit as b approaches infinity of negative e to the u du. Okay? If I take my antiderivative would be e to the u, or negative e to the u, so negative e to the negative x. Don't forget your bounds. So my original bounds were from 1 to b. So integral first, bounds second, limit is last. So now we're going to substitute in our bounds. You have to show that you're substituting in your bounds. Do not skip this step. So I'm going to say negative e to the negative b minus negative e to the negative 1. Now clean this up before you go trying to do anything else with this. I have the limit as b approaches infinity of negative 1 over e to the positive b, because a negative exponent means it goes to the bottom, plus 1 over e. So now that you've cleaned this up, we're now ready to evaluate our limit. So integral first, bound second, limit last. When I direct substitute in, I get negative 1 over e to the infinity plus 1 over e. Now look at this for a second. Remember that e to the infinity is going to get infinitely big. And if a denominator is getting infinitely big, then a number is getting infinitesimally small. So this guy right here, the whole thing is going to go to 0. So what's left? 1 over e. That is the area under that curve. So my integral not only converges, the area under this curve is 1 over e. And we proved that on the previous page in that exploration. So my integral converges. And it has a finite area under the curve, and that area is 1 over e. So let's do one that maybe we haven't talked about in an example. So let's do one that has an infinity in the bottom bound. Now I know an infinity in the bottom bound, when we did it up here, I used a. You don't have to use a, you can use c, you can use d, you can use whatever letter you want. So as long as we get rid of it. So I'm going to set up a limit. I like to use b for some reason. B approaches negative infinity. And instead of a negative infinity, I'm going to put a b there. So we're using a dummy variable to go in the place of where the infinite number was. So I have e to the x over 4 dx. Now this is an integral that would require u sub. U would be x over 4. It is helpful if you think about that as 1/4 times x. du would be 1/4 dx. I don't have a 1/4, so 4 du is equal to dx. So my antiderivative still have a limit. My antiderivative would be 4e to the x over 4. And I didn't bother rewriting it in its u substitution format, but don't forget, we got to sub in those bounds of b to 0. Limit is always last, and you have to write limit at every step of the way. I know that's getting old me saying it, but you're going to want to skip it. Plug it in. So 4e to the 0 minus 4e to the b over 4. And now we're ready to do our last step by subbing in the limit. So 4e to the 0, remember e to the 0 is 1, so I've got 4 minus 4e to the negative infinity over 4, which if we rewrite is 4 minus 4. A negative infinity divided by 4 is still some negative infinite value. And remember that a negative exponent is really going to the bottom. So what's going on is that's really on the bottom. And this number is getting bigger and bigger and bigger and bigger and bigger and going to infinity. So if a denominator is getting bigger and bigger and bigger, then the number is getting smaller. So this quantity is going to 0. And all that's left is 4. So therefore, the area under this curve is 4, and my integral converges. Okay? Now, I really like this next question because I think it's a cool question that applies some previous knowledge. This is an infinite volume question. So we're still going to let our function be e to the negative x. So let's graph that real fast. E to the negative x was the graph that we used a while back. So it's a decaying e to the x function, has the point 0, 1. And it says, let R be the region in the first quadrant between the graph of f and the x-axis. So my function is all of this stuff forever and forever and forever, all the way out to infinity. Now, we're going to revolve this around the x-axis. So what I'm going to get is a 3D shape that when I cut slices, I'm going to get a disk, and it's going to have a radius that is represented by the function. And so because we know our volume formula, our volume for disk is pi integral, in this case, from 0 to infinity, we're going to have infinite disks all the way out to infinity of r squared, so e to the negative x, all squared dx. And so this is an improper integral. It's a volume that has an infinite bound. It goes on forever and forever, infinite disks. And we're going to set it up using a limit. I'm going to take the limit as b approaches infinity of pi integral from 0 to b, insert the dummy variable. I'm going to go ahead and simplify this and say that this is e to the negative 2x, power to power remultiply, dx. So we're going to attack the integral first. We're working from the inside out. Keep in mind, if I let u be negative 2x, then du is negative 2 dx. I don't have a negative 2. So du divided by negative 2 is equal to dx. So I have the limit as b approaches infinity of negative pi over 2. My antiderivative is going to be e to the negative 2x. And we're going to evaluate all of this from 0 to b. So we're going to plug in our bounds next. The limit as b approaches infinity. Negative pi halves e to the negative 2b minus negative pi halves e, and we're going to go ahead and call that 0. We know that anything to the 0 power is 1. So I have the limit as b approaches infinity of negative pi over 2. I'm going to go ahead and move the e to the 2b down at the bottom because the negative exponent means it goes to the bottom. And I have a plus pi halves right here. So after you've plugged in your bounds, we're now ready to evaluate our limit. So negative pi over 2e to the 2 times infinity plus pi halves. And you notice we're in the situation again where here is something that's going to get infinitely large. So if a denominator is getting infinitely large, then our number is getting infinitesimally small. So that quantity is going to 0, and I'm left with pi halves. So here is something that was an infinite bound that had washers that went on forever and forever and forever, but the volume of this thing is pi halves.